I have said this multiple number of times that different subjects of mechanical engineering are related, are connected with each other. And this connection you will realize even better when you learn numerical solving skills. One of the most commonly known or one of the most famous such relationship is between engineering mechanics and strength of materials. In this example, we are going to see that connection. And let me tell you, this is a question which has a very good probability of being asked in GATE this year. The question says that for an iron beam having section as shown, find the width x of the flange. So first part of the sentence is talking about an iron beam which has a section like this. You can see it is an inverted T section, right? This is a T-shaped section. And this you can see is an inverted T section, or simply T section also you can call it. So here what is happening? That here in this section you have to find width x. Where is x? This is x. This is the width x that you have to find, so that the magnitude of maximum compressive stress is 3 times the maximum tensile stress. So wherever in this beam you will have maximum compressive stress, that magnitude should be 3 times of the maximum tensile stress. This is the situation, this is the condition that you have to meet. The member is in pure bending subjected to sagging. As you can see in the cross section or in the section shown, the thickness of this is 0.025, correct? Its height is 0.1 meter, 0.1 meter. So this is the data given to you. I want you to pause this video for a moment and try to answer this question, and then go through my entire explanation, right? Even if you think you have figured out and you know how to answer the question, still it is highly recommended to go through the entire solution. It will teach you a couple of things which will help you in your numerical solving. So if you look at the question, other than the geometry of the section, there is primarily just one additional information you have, which is this. Correct? Means you have to start from that. There is no other way to start. Correct? This relationship would be the first step of your solution, because practically there is no other concrete information available to you. So let us assume that sigma c and sigma t are representing maximum compressive stress and maximum tensile stresses. So as per the question, sigma c is 3 times of sigma t, correct? Which means that sigma c divided by sigma t is equal to 3. Something like this. What now? What next can we do? This is a bending stress, right? Sigma c and sigma t, they are not normal stress as a result of some direct load, but as a direct tensile load or direct compressive load. Rather, they are due to bending. And we know that bending stresses sigma is equal to my divided by I. We know the usual meanings, so I am not repeating that. For any given section, tell me, will the value of bending moment change? No. Any section will have a specific value of bending moment, right? If you have a beam, like the question said, we have an iron beam. So whatever be the type of this beam, any section you pick, at that section there will be a specific value of moment M. We discuss more about that value of bending moment in further units. There will be a separate unit where we will be discussing about bending moment and shear force at a given section of the beam. So the value of bending moment, that value is not going to change whether you pick the top point, or you pick the bottom point, or maybe you pick the neutral axis. So the value of M is same for both. So if I want to put the expression value here in sigma c, M will not change, it will be same as its value in sigma t. What about the value of I? Same, I also belongs to, it's a geometric property, you can say, with respect to a specific axis. That value also is not going to change for a given section. So basically M by I does not change for a given section. which means that if I put this value here and here, what am I going to get? I will be getting, in place of sigma c, m yc divided by I, divided by, in place of sigma t, m yt divided by I. M will cancel, I will cancel, I will eventually get yc divided by yt. So sigma c by sigma t is basically equal to the distance of the point where sigma c is acting, maximum compressive force is acting, that point's distance from neutral axis, that is yc, and the point where maximum tension is acting, that point's distance from neutral axis is yt. So now the question boils down to finding out the expression of sigma c in terms of yc, or you can say yc and yt. Where will the maximum compressive and maximum tensile stresses act? That's something where you need to be careful. How? You may think, sir, that is the very easiest thing to tell, sir. Sir, always at the top sigma c will be there, always at the bottom sigma t will be there. Some of the students form this opinion. Why? Because in majority of the questions, what happens? Majority, I am telling you, load acts from the top. If there is a beam, suppose if there is this beam, on that beam, in majority cases, the load is going to act from the top, which means this beam is going to sag, like this, right? This was sagging, and this was hogging. But in majority of the cases that we discuss, sagging occurs, beam bends like this, which means the top fiber will be under compression, bottom fiber will be under tension. But that's not a universal truth. You can have cases and questions where you may have an upward acting load, or a moment would be acting in such a way that top fiber would be under tension, bottom under compression. So don't make it a habit. And whenever you have been given such question, read the question carefully, what it tells about the direction of the load. For example, in this question, it told you directly, pure bending is occurring subjected to sagging. Means the beam is going to bend like this. Means the top fiber would be under compression, bottom fiber would be under tension. Let us apply this concept in finding out the values of yc and yt. Yc and yt values will be calculating from where? From the neutral axis. So from the neutral axis, let's say the neutral axis could be somewhere here. From the neutral axis, the distance of this is the point where sigma c is going to act in sagging. This is the point where sigma t is going to act in sagging. So yc is effectively this distance and yt is effectively this distance from the neutral axis. Let us denote them using a proper diagram and put their values. In this section, let us assume that neutral axis is passing through this point. So this dash is showing the neutral axis, okay? And the distance of this neutral axis from the bottommost point, which is sigma t, right? Let's say that is y bar. Let us say y bar is the distance of bottom fiber from the neutral axis. Got it? So this distance is y bar. And how much is this distance? Let's say this distance is denoted by a. Okay, practically a is equal to h minus y bar, right or not? H is the total height from top to bottom point, minus y bar is equal to a, correct? So that defines the position of neutral axis from the point of view of this section. Now, since it is subjected to sagging, so topmost point would be under compressive stress sigma c, correct? So if we draw its stress variation across the cross section, the bending stress variation, so we know that the point or the sections above neutral axis in sagging will have compressive stresses. So this is how it is going to look, the compressive stresses in the portion above the neutral axis in sagging, and the portion below neutral axis in sagging will have tensile stress, something like this, correct? So this is how this entire section's division of stress is going to look like. Please note, exact value we don't know yet. We don't know what is the value of y bar or a. But there's one tip that I would give you here. that in majority of the questions which involve bending stresses, at some point or the other, you may have to find out the position, the location of neutral axis. Like in this question, it did not mention anything about neutral axis, right? It's not asking you where is neutral axis, but it has given you the relationship between bending stresses, sigma c and sigma t. And eventually, see, you will have to find out, right? These values which we have found out, the value of a and y bar, those values you will have to put here, na? Because sigma c is by sigma t is equal to yc by yt. And what eventually we calculated, what eventually is the value of yc? Yc is equal to a and yt is equal to y bar, correct? And what is a? A is h minus y bar, and this obviously remains y bar. So you see, these values from neutral axis are eventually going to become a part of the calculation. But this is something that you can do inherently as a default mode in the questions of bending, where if suppose a very difficult question came and you are clueless, you have zero clue how to start the question, what to do. Start by locating the neutral axis. It's a generic tip. Obviously, there will be 1 to 5% questions where this may not work, and there you may have to go by the other methods and ways that we have discussed and we will discuss. But in majority of the questions of bending, position of neutral axis becomes, that calculation becomes a part of the calculation at some point or the other. So if you are clueless in a question, the most obvious way to start the questions of bending would be the position of neutral axis. So in this question, as I told you, yc and yt values will eventually come out to be h minus y bar divided by y bar as per these notations. H minus y bar divided by y bar, right? That is equal to sigma c by sigma t, which is equal to 3. So putting this value here, this is what we are going to get, correct? This is what we are going to get, h minus y bar divided by y bar. Now what needs to be done? Let us now simplify this and see what we get. So h minus y bar is equal to 3 times of y bar. This y bar goes on the right side, becomes 4 y bar is equal to h, correct? Which means y bar is equal to h divided by 4. The value of h is known to us as 0.1 meter, correct? That value if you put here, the value of y bar you will get as 0.25 meter. I think it's meter and not mm. And since a is equal to h minus y bar, so putting the values, this would be 0.1 minus y bar is 0.025 meter. That gives you 0.075 meter as the value of a, this value, correct? So now we know the position of neutral axis. Where does it exist? Where does it is going to pass from? From the bottom, a distance of 0.025 meter. If you look at this actual section, where does the point lie? This height is 0.025 meter, this, right? It means that neutral axis is going to pass from here, from this point, right? This is the point from which neutral axis is going to pass. Clearly, neutral axis is dividing the section into two clear rectangles. This is the vertical rectangle, this is the horizontal rectangle, right? So this is how it looks like. Right? Neutral axis passing from here, and consequently the stress variation diagram will also change in a way that at neutral axis its value now becomes 0. So we have found out the position of neutral axis, right? It is going to pass from this point, and now question is asking, find out x. This is slightly counterintuitive. Generally, neutral axis we relate with the vertical dimension, right? In such vertical loading. But here question is asking you to relate neutral axis position with the horizontal dimension, which is something different than we usually do. How to do that? How to relate these two things together? This is where you have to recall the link between strength of materials and engineering mechanics that I told you in one of the previous lectures. Recall that we have covered this expression. Correct? I clearly mentioned that this expression, its application, you will see its utility when combined with engineering mechanics, right? Let me bring a very basic concept of engineering mechanics, which is the concept of centroid. We have used that concept already in strength of material, the derivations of neutral axis. We have used that concept already, right? So here we are going to apply the same concept. Let's divide this expression, divide and multiply with the area of the section. So if we do that, this is what we are going to get, correct? Both of them can get cancelled. Eventually it's the same expression. So we have multiplied and divided with that. This area we will write here, dividing it directly with this integration. So this is how it can be written. Again, effectively the same expression. And as we know, in the centroid calculations, the position of centroid is calculated by this expression, correct? So which means that this part here, integration y dA divided by area, is nothing but the position of centroid. So this we can clearly write for this expression, right? The area multiplied by the position of the centroid about neutral axis should be 0. Why is about neutral axis important? Recall, this expression was about neutral axis. Hence, this expression also is going to be true about neutral axis, which means we will divide the entire section into above neutral axis and below neutral axis. And for above neutral axis, we will write this expression. And for below neutral axis, we will write this expression, and both of them combined, their summation should be equal to 0. This is what this expression means, just like this expression, but a slightly modified form using the concepts of engineering mechanics. If we do that, what will we get? This is the expression. As I told you, we will divide it into two parts. This product of area and center of centroid position. For the top part, let's say above neutral axis, this region I am calling as top, which is above neutral axis, right? This is the neutral axis. And this part I am calling below neutral axis as bottom. So this product for top plus this product for bottom should be equal to 0, This is what it means, correct? Or in other words, what we can do? In other words, we can write that this product for top is equal to this product at bottom. How? Let me tell you that if we do the calculation of YC, about neutral axis, its value for the bottom part will come out to be negative. Bhai, this is the reference line. If this is the reference line, then let's say here is going to be the centroid for the upper part. So this is going to be positive, and here is going to be the centroid for the bottom or the lower part. This is going to be negative. So eventually this calculation, when you put the values, this will come out to be negative here, which means that this part you can write on the right hand side. We will not consider negative sign. Of YC. We will just find out its magnitude, but we will put it on the right hand side. That we can do. Always remember, this is some of the very basic concepts. You use this in multiple places across subjects. A very commonly used way is to equate the forces acting on the right hand side and the left hand side, or the moments acting clockwise and counterclockwise. So either you can do that, you will consider all counterclockwise moments as negative, and you would write clockwise moments which are positive, and counterclockwise moments which are negative, but this you will put with a sign, and then you will say net moment is equal to 0. Both of them will cancel, you will get net moment as 0. Another way to do this is that you will not consider sign, you will not consider which is plus, which is minus. You will simply write that clockwise moment is equal to counterclockwise moment. Both of them are same. In the first part, you were writing this as plus, this as minus, and equating to 0, correct? Or you are forgetting about the sign, which is plus, which is minus. You are simply equating them. Both of them are the same equation. You bring it on the right hand side, you will get this. But the approach is different. Whatever approach you want to choose, you can choose there also, here also. This also is the same way. Either you can say that no, I will take the reference from neutral axis and the position of this YC, I will count positive and negative. You can do that. And you can use this expression where eventually yc bottom will come out to be negative. So this sign would become negative. That is one way this equation of summation is equal to 0 is used when you consider plus and minus sign. But when you are saying I don't want to consider plus minus sign, I will only consider the magnitude of yc. So in that situation you can simply equate the top part of ayc with the bottom part of ayc, again which is something which you will eventually get from here, right? If this part you bring on the right hand side, you will eventually get this same thing, ayc is equal to ayc for top and for bottom, correct? But now we will not be considering the plus and minus sign. Okay, please note that this thing that I told you, it's not something, I'm repeating it, is not something specific to this calculation or to this topic or to this concept. This is universal. Wherever you are going to consider sign for forces, for movements, even in non-design subjects, you will see that, where we will be dealing with heat and work. There also you will see that in subjects of thermodynamics, for example. Okay, so this is what we have got now. For the top part, ayc will be equated with the ayc for the bottom part. What is its value for the top part? Area is this value, means this height. Let's say, how much is the height? Height is 0.075. We already calculated, right? A minus 0.025. So this is the height and width is 0.025, which means that this is the area, 0.075 multiplied by 0.025, and the position will be at the center. It's a rectangle, means the position of its centroid will be from neutral axis, where 0.075 divided by 2, 0.075 divided by 2. Please note one thing, I would remind you about one thing. We are doing the calculations from this point, from this line. Why? Not everywhere. Don't do this mistake that whenever you got this question of T section, whenever you got the T section question, you started doing the calculation from this point. Don't do that mistake. This is something we are doing because neutral axis value, the position was passing from this point. If neutral axis maybe was passing from some other point, let's say it was passing from this point, then we will have to do the calculation about that point. We would get the answer. It would get slightly complicated, one step additional calculation. Right now they are simple rectangles, right? About this point, you have simply one rectangle on top, other rectangle on the bottom, because this line is dividing it into two simple rectangles. But if neutral axis was not passing from this point, then it will pass, let's say, from here, then top part is still a rectangle, but bottom part is not rectangle, right? So that calculation of ayc, again you will have to split into two parts. So that would add one step, but concept will be equally valid. Coming to this discussion here, for the top part, we have written this expression. For the bottom part, again, how much would be the area? X multiplied by 0.025. That is the area, x multiplied by 0.025. And how much would be the value of yc without sign? Don't consider sign, we are now equating their magnitudes. It would be 0.025 divided by 2. This length, correct? For rectangle, we know that centroid lies at the center of the area. So 0.025 divided by 2, that is the value of yc. Now what? Cancel this, cancel this, cancel 2, cancel 2. Solving it, you are going to get x is equal to 0.225 meter, means 0.075 multiplied by 0.075 divided by 0.025 is going to give you 0.225 meter. That's the required value for this width x.